The transition from traditional programming to machine learning represents a specific architectural shift. For decades, software engineering relied on a single premise. Humans abstract real-world logic into hard-coded if-else control flows. We write the rules, and the computer executes them. This approach fails when a system's required rules are too complex for a human to perfectly define. Handwritten digits are a classic example of this complexity. Their varying stroke weights and structural inconsistencies are simply too numerous to capture in standard code. Spam email filtering presents a similar problem. Defining every possible variation of a scam email using static rules is impossible at scale. To solve this, computer scientist Tom Mitchell proposed a system that improves its performance on a specific task simply by ingesting more experience data. This is the core inversion. We are moving from writing explicit execution rules to engineering systems capable of deriving their own rules from raw data. Let's deconstruct this transition by building a spam filter using a traditional software loop. A human developer manually inspects emails and identifies patterns, like the word free or the phrase for you. We translate those patterns into explicit heuristic rules, instructing the program to block messages containing those specific text strings. The system is tested against known spam. When it fails, the developer has to manually patch the logic. This creates a bottleneck in a fluctuating environment. Spammers adapt. They replace for you with for you, bypassing the hard-coded filters. Developers must then continuously write and append increasingly complex rules just to catch these new variations. Eventually, the codebase becomes a list of fragile heuristics that are difficult to maintain and slow to deploy. Rule-based systems are structurally incapable of surviving in adversarial environments without constant human intervention. Supervised machine learning provides a direct architectural alternative to this manual loop. Instead of writing rules, we provide the system with a dataset of examples paired with their desired answers, known as labels. The execution block changes. The algorithm analyzes the dataset rather than executing human logic. The algorithm mathematically computes its own probabilistic predictors, such as word frequencies, to detect spam. This derived logic allows the system to handle problems with no known mathematical solution, effectively generalizing to data it has never seen. This results in a drastically shorter codebase compared to the previous list of manual heuristics. In supervised learning, the dataset becomes the engineered logic, eliminating the human bottleneck in rule creation. However, even an ML model can decay if the underlying behavior of the data changes after the system is deployed. We address this through online learning, an architectural pattern that creates an automated feedback loop. Live user actions, like flagging new spam, flow back into the system to retrain the algorithm dynamically. Now consider a different challenge, possessing massive amounts of data but lacking any predefined labels to train on. This requires the unsupervised learning paradigm, where the algorithm must discover inherent structure without a teacher's guidance. Clustering is a core unsupervised task, used to segment data, for example, grouping blog visitors by their reading behaviors. Anomaly detection is another unsupervised application. It maps normal behavior and flags outliers, such as fraudulent credit card transactions. Between online adaptation for temporal shifts and unsupervised clustering for structural unknowns, machine learning provides the tools to handle data across varying states of supervision and stability. Viewed as a complete engineering landscape, machine learning functions as a specialized toolkit, with each architecture mapped to a specific data requirement. We can categorize the ecosystem into a matrix based on data availability and environmental stability. If you have clean labels and need distinct answers, you deploy supervised classification. If you have unstructured data and need to discover hidden relationships, you deploy unsupervised clustering. For static problems, you use batch models. For rapidly shifting environments, you architect an online feedback loop. The choice of machine learning architecture is dictated entirely by the shape and flow of your data. This defines the modern engineer's mandate, transitioning from writing precise execution logic to curating data pipelines and defining performance metrics. Mastering machine learning requires relinquishing human control over explicit rules. When we stop writing the logic ourselves, we build systems that discover the logic we cannot see.